the order just for smidgen here. I'm going to scoot forward to 6K where um, we find the general solution of our circular functions. So you'll notice on our calculator sometimes when we solve our equation and we don't restrict the domain, we get answers in terms of n. Okay, that's our general solution. Now I'm going to show you the process by which we use the general solution. There's my sine one, there's my cos one, and there's my tan one, because historically and over the past few years, I've noticed that some of the boys prefer to use this all the time instead of, doing a unit circle and going around the circle. So let's use the general solution. So for tan, and I'll explain the general solution to give you an idea of how to remember the rules a little bit later. But don't forget that if you're tech free, you're going to have to remember these rules if you want to understand or use the general solution. So there's my solution. So what we're saying is, okay, so tan inverse of root 3 is equal to, we just put the value, what angle is that? So we'll assume we're working in radians, that's pi on 3. So that means my x, which in this case is 3x, is equal to n pi plus tan inverse of a, which in this case is pi on 3. Okay, so typically we try to simplify that a fraction. If I take pi on 3 out the front, that leaves me with a 3n plus 1. All right, now that's what 3x is, so x is equal to, if I divide by 3, I get pi on 9 times 3n plus 1. So that's my general solution, okay, and that's typically how we would want the answer expressed if you've been asked for a general solution. So that's fine, but even at this stage here, okay, if we decide that if you just want to get some answers and we put that x is equal to n pi plus pi on 3 over 3, and then if I just put n equal to 0, to start with 0, I get pi on 3 over 3, which is pi on 9. If n is equal to 1, I get pi plus pi on 3, which is 3 on 3 plus pi on 3, which is 4 on 3. 4 on 3 over 3 is 4 pi over 9. I could put n equal to negative 1. And that, so if I fill that out, I get negative pi plus pi on 3 over 3. So negative 3 plus 1 is negative 2 on 3, which is negative 2 pi on 9. So there's my solutions there. So instead of necessarily going with the, there's my unit circle, tan is positive there and there, the angle I'm looking for is pi on 3, and go around. Okay, so then 3x is equal to pi on 3, 4 pi on 3, etc. I can just go into this, find my general rule, and substitute values in. So for some of us, we prefer that as an answer. All right, so I guess we're highlighting in here two kinds of questions. One, there's my general solution, okay, and then you can use that general solution to find specific values. All right, so let's have a look at the second one. My sign rule is slightly different. Okay, we have two possibilities here for the sign. Okay, and as I said, I'll explain that as we go. So let's work out the angle first. So sine inverse of 1 on root 2 is equal to pi on 4. So what we're saying is the angle x up here, all right, so in this case, x is given by that expression. So we'll say x minus pi on 6 is equal to, there's my rule, 2n pi plus sine inverse, so it's equal to 2n pi plus sine inverse, which is pi on 4, or I'll come here, x minus pi on 6 is equal to 2n plus 1 pi minus sine inverse, which is pi on 4. So if you like, there's two separate little rules there to give me both my answers. all right? So now I just rearrange, take pi on 6 across, so I get 2n pi plus pi on 4 plus pi on 6, and my second equation, x will be equal to, I might expand this bracket first just to make life, to get the rule a bit easier, 2n pi plus pi minus pi on 4. Don't forget to bring the pi on 6 across, which is plus pi on 6. So now, again, that's 1, that's 2. Number 1, x is equal to, well, pi on 4 plus sine pi on 6, they're both on 12, aren't they? So it becomes a 3 plus a 2. So it's 2n pi plus 5 pi on 12 is one equation. We've got a pi minus pi on 4, which is 3 pi on 4. Make them both over 12. So that's over 12. So it becomes a 9 pi plus 2 pi. So x will be equal to 2n pi plus 11 pi on 12. Okay, so at any stage along here, whether it's this equation, I can stop, just put n equal to 0 or 1, 2, 3, whatever value I want to get my solutions. If I want the formal general solution, again, let's take pi on 12 out the front. Yeah, I think pi on 12 is the best one. So that leaves 2n in the middle times 2. So that becomes 24n plus 5. So let's just check that. If I multiply pi on 12 back through, I get 24 over 12, which is 2. I get 2 pi on n, which is that term. 5 times pi on 12 is 5 pi on 12, which is that term. Okay, so that's one solution. The other solution, do exactly the same thing. You bring that pi on 12 out the front, the fraction. Multiply this term by 12, so I get 24n plus 11. That's my other solution. Okay, so if I put n equal to 0, I get, what do I get? I get 5 pi on 12 and also 11 pi on 12. Then if I decide to put n equal to 1, and you just, to get the range of values, you want 24 plus 5 is 29. 24 plus 11 is 35. So you can see both of those are greater than 2 pi, so typically you may not use them. Then we might subtract 1 to get smaller values or negative values, okay? So they're my general solutions. That's what we're looking for, something in that format if we're asked to find the general solution. Actually, I've got to read the question, don't I? The question's actually asking us to find the first three positive solutions. So I've nearly found them in the first one. I've got the first 2 there. So maybe if I put now n equal to 2, n equal to 2 in my solution, I get 6 plus 1 is 7. 6 plus 1 is 7 pi on 9. Okay, so that's the third positive solution. I've got 1, 2, the first 3 positive solutions there. Okay, so don't forget, I guess I'm just highlighting that we can use either for. All right, for my final tan function again, a similar thing. I've got my angle x minus pi on 3 is equal to n pi plus tan inverse of a. So tan inverse of 1 on root 3 is pi on 6. So take pi on 6 out the front, and I get 6n plus 1. Oops. Before we do that, maybe we're better off. Let's take that minus pi on 3 across. So I'll scrub that out. So we'll go x is equal to n pi plus pi on 6 plus pi on 3. common denominator, so it comes 1 plus 2. So we get x is equal to n pi plus 3 pi on 6, which is pi on 2. So x is equal to pi on 2 at the front, 2n plus 1. All right, so again, there's my general solution. If I want the first three positive solutions, I put n equal to 0. I get pi on 2, n equal to 1. I get 2 plus 1 is 3, 3 pi on 2. And if I get n equal to 2, I get 4 plus 1 is 5, 5 pi on 2. Okay, so my first three positive solutions. If you want to try to remember the general formula themselves, let's come up here a bit. If I consider where I try and solve for cos, for sine. So normally that's my angle there, say pi on 6, and the angles I'm looking for are from there and there, aren't they? So as I travel around my unit circle, it's 0 plus pi on 6, pi minus pi on 6. Come around 2 pi plus pi on 6, 3 pi minus pi on 6, 4 pi plus, 5 pi minus. So in other words, it's even number times pi plus the angle, and then it's the odd number, which is why we do the 2n plus 1 minus the angle, which is what we've got here. I reckon the sine one's the hardest one to remember. So 2n plus 1 make sure we get an even number. So it's pi, 3 pi, 5 pi, 7 pi, minus pi. And then we subtract the angle because we're going back up into the second quadrant. This one here, 2n pi, make sure we get an even number, 0, 2, 4, 6, etc., plus the angle. So that's how that general solution comes about. If I consider cosine, angle is there, angle is there. So it's always an even number, plus pi on 6, even number minus pi on 6, which is what we've got here. If the cos, it's the even number plus cos inverse, even number minus cos inverse. And we can do the same thing for tan. So in some ways, it might be one of those ones where we memorize. If you want to solve it this way all the time, just remember those rules. Don't worry about going around your unit circle, etc. Just remember the rules, okay? Otherwise, if we have to come up with a general solution, often it's a tech active, so often you have the formula access to write down, all right? But anyway, I thought you'd show you this method nice and early in case you want to practice it and solve all your trig functions in that way.